Right, let's begin. And then we should get a start on the next chapter today as well. So, Young's modulus. Oh, for goodness sake. Oh, come on. Young's modulus. Question? Problem? No? Okay, do you write that down? Yep, Young's modulus. Okay. So, Audrey, you got my YouTube replies, yes. Yes.
You reply to YouTube comments faster than you reply to emails.
Yeah. And you've learned something very important, I think. So, have you considered sending your essay to me as a YouTube comment? Just think about it. Yeah. Just find a video and put a comment on it, and I'll go, ooh, YouTube comment, exciting. Okay, Young's modulus. A few definitions before we begin. I'm sure somebody knows this, although maybe it's a bit too hard. Deformation of a material. Does anyone know this word, deformation? Now look at the beginning of it. Deform, yeah. So what would that mean? Deformation of a material. Changing the shape, yeah. So the deformation of a material is the process of changing the shape. And for us, that shape change is the length. But not only is it changing the shape, it means changing the shape by the means of using what's called a stressing force. So if I take something like this and deform it, the deformation is the process of changing the shape by using a force, a stressing force. That's deformation. Can you see okay over there? Yep. Continue? Not yet? Okay. Yep. Got that? Bruce? No. Okay. So, now we have deformation. This is kind of the concept for the lesson. We have these two, what would you call them? Two things we can do to a material when we deform it. We can have what's called the stress on a material. Now, we use stress in English to mean, like worry, but in physics, stress has an exact meaning. I wonder if anybody has studied or have heard this word in physics before, stress. Maybe you have, maybe you haven't, because it's more of an engineering word than a physics word. Does anyone know stress on a material? New word? Yeah? Kinda, not too far away from it, yeah. Stress on a material is the force per cross-sectional area, which is kind of like a pressure. In fact, really it is a pressure, because the formula is force over area, but then you realize, oh, that's Pascal. Therefore, clearly the unit of stress is Pascal. But there is a small difference with pressure. So we talk about pressure like in a room, whereas for stress we talk about stress inside the material. I'll just draw you a quick picture to show what I mean. So if you have a material and you're applying some force to it, and this is called the cross-sectional area. then the stress is the pressure over the force over the area. But that's an internal phenomenon, whereas pressure that we've used in the past, that's external. So stress is always inside or at the end of a material. Pressure is something usually external. Oops. Okay. So stress is force over area.
What's an example of stress?
The example that we usually deal with is when things hang from the end of a rope. So the force is pulling down on the end of the rope. The stress is like inside the fibers of the rope. It's the force because of the weight and the area of the rope. That's a bit different to the pressure, because the pressure would be like the air pushing on it from the outside. So like with my pen, when I pull this down, there's a stress here, and it's the force divided by the cross-sectional area. Whereas if I said the pressure on the pen, I would mean like from the air. Yeah.
The force will be acting down, upwards.
It depends where we're looking at. So like if I'm looking at the end, there's a force pulling down. But if I'm looking at the middle, it depends which side I'm looking at. So if I'm looking from underneath, that's different to if I'm looking from down below. It really doesn't matter, because for what we're going to do next, they'd be the same anyway, so it doesn't matter. I guess if I'm looking from underneath, it's down, and if I'm looking from the top, we're seeing the reaction up. But it doesn't matter. It really doesn't, because stress is a scalar. It is, I should really have said maybe the size of the force. We don't care about the direction, because it's always in the perpendicular direction.
Area should be cross-sectional.
Cross-sectional area as well, yeah.
Is stress similar to tension?
Tension would be the total force. The tension doesn't care about the area. So you could say actually, yeah, if you want to say stress is tension per area, if you want to put it that way. Yeah. Cross-sectional area, yeah. By cross-sectional area, I mean this area. So like, for example, when you talk about a shape, if I said the area, maybe you mean this area. But cross-sectional area means exactly the area here on the face. Yeah?
If the force is...
Yeah, is that way cross-section? No, that side, yeah. It's perpendicular to the force, yeah. Yes, continue. You have this? Yep. Oops, not this. You have this. Okay. Well, the next one is the strain on a material. You're making that face. You're making that face that I don't like what Stephen is doing face. Yes, you need to know these definitions. These two definitions, stress and strain.
Okay.
I know, but you should still know this word, because it could be used in a question. You don't want to look at it and go, what the heck is this?
But will they ask like what's the definition of strain?
Definition of strain and stress, definitely.
Deformation?
No, because it's no. But I mean, what would you say deformation is? Yeah, they're done. You know the definition. But it's not a physics definition, so I give that definition for your English, not for your physics. Yeah? Continue? Does anyone know strain? We just did stress. Does anyone know strain? Force over area was stress. So what's strain? Does anyone know this one? Strain of on the material is the change in length that's taken place compared to the original length. In other words, mathematically, it is simply the extension over the natural length. That is the strain. The extension over the natural length is the strain. Yeah? I mean, what unit is strain? Strain is the proportion. Okay, if you want. Okay. Strain is the extension divided by the natural length. If you're going to give me a hard time,
No unit.
no unit, correct.
Well, the extension doesn't have a unit.
No, the extension does, and the length does, but they're both the same unit, because you measure extension in meters and length in meters.
Yeah, and it's a change of.
Yeah, but if you look at it, what's the units on the top? Meters.
We cancel them.
You cancel them, yeah. So actually strain has no units, it's unit free. Yeah? Continue? Well, I might have something under this to say. Note that strain is unit free. Is that orange too hard for you? I do? Ah, yeah. Okay, once I reply to his spam, I need to remember to bring you chocolate.
So never.
Huh?
So never.
No. Maybe I'll reply to you, but then just forget about the chocolate.
Okay, just remember what chocolate I forgot about.
No.
You want chocolate?
You don't get any marks for chocolate, so it's okay. You can take the loss. Okay, continue? Yeah? So, Young's modulus E, unfortunately the same letter as energy, Young's modulus E is the ratio of stress to strain. In other words, we say Young's modulus is the stress divided by the strain. You are struggling so much with that orange. I've never seen somebody defeated by an orange. Yeah. Way versus orange. Orange wins. Flawless victory. Have you eaten one slice yet? No, flawless victory for the orange. Okay. Yeah.
What's
The units?
abbreviation of stress and strain? It's the letters we're using.
Oh, do you know actually, in the formula book, I think they use just the word stress and strain. Although there are letters for it, I don't remember what. I think, I can't remember, I think one of them is like a sigma or something. But we don't in the formula book use any special letters. Okay, so why is this important? Well, what Young noticed is that if you apply a force to a material, it will change its length. So what he noticed was it doesn't matter what force he used for a material, if he calculates the stress. Okay, so let's say you're changing the force. Will the stress change? Well, yeah, because what's the formula for stress? Stress is force over area, isn't it? So, if you change the force, will the stress change? Yeah, the stress will change because you're changing the force, and stress is force over area. Now, will the strain change? If you have more force, will there be a different strain? Well, yeah, because if there's more force, what will happen to the extension? More. So then extension over the length should be more. But what Young noticed was it doesn't matter what the force is, the stress and strain ratio stays constant. for every material. So even though the stress might increase, the strain would increase as well. Or if the stress decreases, the strain decreases. But the ratio between them is a constant for each material. So for each material, it has its own what's called Young's modulus, a constant for how the stress and strain are related. So we need to try and understand what the Young's modulus is telling us. For example, if the Young's modulus is big, what does that mean? If it's small, what does that mean? So let's examine this in a bit more detail. Can I continue? Do you have this formula? Yes? Oh, what are the units for E here? Pascals, yeah. Okay, so just before we go on to that, what exactly is Young's modulus telling us? Well, it's stress over strain. What's the formula for stress? Force per area. And strain?
Tension over
length. Now, because this is a stretchy material, we can probably use Hooke's law for the material. So what did Hooke say F is? K times extension over area over extension over length. Yep. So what can I cancel here? Axis. So I'll be left with K L over A when you simplify it down. Now, does the length, the natural length, change? No, because the natural length is a constant for the material. In the experiment, doesn't change. It's the same. Does the A change? No, it doesn't really change. Now, you might say, well, it does. If you really pull it tight enough, the A might get smaller. But we say it doesn't change. So, Young's modulus, this is just like a constant. Young's modulus is proportional to Hooke's law constant. In other words, a big Young's modulus can have the same meaning as a big Hooke's law constant. And if you remember, if K, or maybe I didn't actually say it, but if K is very big, or if E is very big, what that means is the material is very stretchy. You know, you pull it a little bit and it really wants to snap right back. Because remember, K is in newtons per meter. So if it's really big, it means you get a lot of newtons for your meter. Yeah? So what material would have a high value of K or a high value of E? What's a really stretchy material? A rubber band, maybe? Yeah, and what would be something with a low K or a low E? Stone, yeah, stone would be, yeah. Okay, so Young's modulus tells us the stretchiness of a material, just like Hooke's law constant does. Big E means stretchy and a small E means not very stretchy. Can I continue? I wanted to give some explanation of what it is. It's a stretchiness measurement. Okay. So, more definitions now. Tensile strength.
Is this the last definition?
I don't remember how many definitions there are. This is, and before you ask me, this is an exam definition.
This is?
Yeah, tensile strength. Does anybody know tensile strength? No? No. Tensile strength is a measurement of the force required to pull something like a rope, a wire, or a structural beam to the point where it breaks. Simply put, the tensile strength is the force required to break something that's used as a support, like a rope or a beam or a leg of a chair. It's like the breaking point for the support. So obviously this is important to know in engineering. If you build a bridge, you want to know the tensile strength. How much force will bring the bridge down?
When I put this box.
Yeah. We don't really say tensile strength for that because the pencil's not used to support anything. We use this language when we talk about materials which are support, like a rope. or a bridge, things like this.
This is a constant.
For the material, yeah. So different materials will have a different tensile strength.
Is this changes?
It's different for each material.
The same object.
Huh?
On the same object.
Yeah. So it just depends on what the material is. So wood has a certain tensile strength. Yeah. Huh? Go on.
The bigger the case, the more stretchy.
Stretchier, like more rubber-like, and a small K would mean more like stone-like, more plastic-like. Yeah. So, what material would have a high tensile strength? What would you say is a strong support material? Steel would have a high tensile strength. Yep. What else? Think about materials that are used for support.
Stone.
Huh? No, go on, yeah. Stone would be quite high. Yep. Huh? Can't quite hear you. Concrete, yeah, that would be quite high. Maybe not as high as stone, I'm not sure. Depends on the stone. Anything else?
Platinum.
Huh?
Platinum.
Yeah, platinum. I think platinum should be high, yeah. Adamantium, you know. Yeah. Of course, that's not a real material. But in the X-Men universe, I think they said that is the material with the highest tensile strength. I don't think you're able to break it. Huh? That's also quite high. Is that higher or lower than adamantium? Higher? So you're saying if Captain America was fighting against Wolverine, Captain America and his shield would win? That's the claim you're making? That's an outrageous claim. Clearly Wolverine would win. Clearly. Okay, so tensile strength, breaking point for material. I was watching a very interesting show a while ago where they were looking at tensile strength of bridges. Now you probably, if you've been outside of Dublin, you'll notice that there's a lot of stone bridges in the countryside. So these are very old bridges and they're just made by just stacking up stones, and they'd be put together in an arch like this. And when people make a steel bridge, we know the exact tensile strength, we know how much force would be needed to bring the bridge down, because we know what it is for steel. When we make a rope bridge, we know what it is for rope. But the problem with these old stone bridges, you know, they may be 300 years old, we don't actually know the tensile strength for these stone bridges, because when people built them, you know, they were just putting stones together. It's not like they were doing any measurements. So the engineering department for the government, they got permission to break one of these bridges to see what would be the limit, what force would you need to break it. So the way they did this was they placed these arms into the bridge, and these were all connected to like huge building machines, and basically they just pushed these arms into the bridge until the bridge would break. By the way, these bridges are kind of small bridges. They'd be maybe like 5 to 10 meters. So they increase the force until it breaks. And quite amazingly, they could not produce a force strong enough to break this bridge. And the total force that they had on it was as if there were 10 HGV, you know those huge shipping trucks, container trucks, you know the big ones you see, with the little cabin in the front here. It was as if 10 of these was on top of the bridge, which of course would never happen because it's only big enough for one. So it means that this bridge should not collapse under normal use because you would need 10 of these. Well, in fact, even 10 of them was not enough because it didn't break. So my point is, sometimes for materials it's not actually clear and you might be surprised by the tensile strength. So I think stone actually can be very, very high, higher than concrete or steel. So those old stone bridges you see in city centres, they would be safer to be on than the concrete or steel bridge, if you can imagine that. So that's tensile strength. Do you have this one? Yeah. Okay. So let's look. Well, we kind of talked about this a little bit. How the E and the K are related. So the E and the K are related because they're proportional. A bigger K means a bigger E, and a bigger E means a bigger K. When we make graphs of stress and strain, if I put stress here and strain here, I'll get a graph, and if I put strain here and stress here, of course I'll get a graph. If you remember, Young's modulus is stress over strain. In this graph here, what's the slope, the gradient? It would be 1 over E, and in this one here it will be E. Yeah, so I think if you can add these two graphs to your notes just quickly before we go on. Do those two graphs? Yeah. Yep. Continue? Yep, okay. So, now, we should talk about some values of Young's modulus. So, we'll measure in pascals, of course. So let's start with rubber. I think I said something wrong to you earlier. I said the bigger the E, the stretchier it is. That's not really the right word. Stretchy isn't even a real word anyways. Stiffness. I need an English word that describes that it's difficult to stretch something. I know, but I want a nice little word like stretchy, but I don't know, too fancy. Not quite, too simple. Something in between. No. Okay. All I can say is the bigger the E, the harder it is to pull. When I realised when I said stretchy, I didn't know if you were picturing it's easy or hard to pull. If I say stretchy, are you imagining I mean it's easy or hard to pull it? Okay, so I shouldn't have said stretchy. So I need a word that means it's hard to pull it. Unstretchy? Stiff? No, because stiff means like it can be solid nearly. I'll just say unstretchy. The bigger the E and the K, I need a word for this.
You can say the smaller the E, the stretchier.
Well, if you want to use stretchier, then yeah, you can say the smaller the E, the stretchier it is. But I don't like stretchy now anymore because it can be confusing. I need a different word. It's not worth it. Just say the bigger the E, the harder it is to stretch it.
Bigger is hard.
Harder to stretch it. Yeah. More exercise to stretch it. Harder to do. Big E or big K means harder to stretch. Yeah? Okay. Because of like what I said, you get more newtons per your meter. So that means you need more newtons per meter to stretch it. Yeah, weird. I thought there was a nice English word to describe this. I'll ask an English teacher. Anyway, let's have a look at some values. So the first one is rubber, and this has a Young's modulus of 0.1 times 10 to the 9 pascals. Continue. Next material is nylon, which is a value of 2 times 10 to the 9 pascals. Does anybody know what this material is?
Surrender.
Huh?
Surrender. Transparent.
Is it? I don't think it is. Or if it is, I never knew that before. I was thinking of something else. It's in the saran wrap? They put in
No,
some...
because like some people call it nylon.
Really? I'm gonna Google this when I go home. It could be because it has that kind of stretchiness to it, so it's a bit like rubber in that you can stretch it. I didn't know that they put it inside of it, but they must put something in it to make it stretchy. Anyways, I was thinking of something else. Anyone else? No? I'm expecting you four to know. Yes? Huh?
Pen.
For what?
Panty?
What?
Pen.
Yeah, what are these called? You see, none of you have dresses on.
Okay, that's all.
So then you don't know. It's the material for the tights. The-
Leggings?
like leggings, yeah. What?
Menstruation pad, because you said 4 of us know it.
Yeah, no, I was thinking of tights. Like leggings. That's what I was thinking of. I don't know about that. Excuse me, guys. Do any of you wear leggings or tights?
Leggings, kind of like what Yona wears, right?
Oh, no.
Inside.
Yeah.
This thing.
No, not this is not leggings.
Oh, the transparent one.
Yes.
Oh, you know the socks are transparent.
Yeah. Stockings.
Yes, Tom.
Yeah. I don't think these guys wear them. I don't think so. I hope not. Anyways, this material is in a lot of. It's not just in stockings or leggings or tights. It's in a lot of clothes. So as you noticed there in your socks, this nylon is in it because that's what gives it the stretchy snapiness to it. In fact, even in your clothes that you wear, like you see my sweater, it has a bit of a stretch to it. It's probably because maybe it's 10% nylon, you know. So nylon is used a lot in clothes. Now you said it might be used in saran wrap, which like the wrap around your food. I could believe that. I'll need to check it, but it does sound right because it has that kind of same stretchy feel to it. But if it is in it, it might only be very small, like 1%, because when you stretch it, it doesn't snap back, you know, and the nylon gives it the snap. Yeah. Okay, so that's nylon. Next one is wood, which you can see is, now we're starting to get to materials which are harder to deform. And as the deformation gets more difficult, you can see that the Young's modulus is increasing. So can you see that this is about 10 times bigger than this, and this is about 10 times bigger than that? Well, I know it's only 5, but we're jumping up in about tens nearly. So the next material is again another step above. This is glass, which is even more difficult to deform. And not only is glass difficult to deform, it has a low tensile strength, which means when we try to deform it, it could break easily. Yeah. Next material after glass is brass. What's brass? It's like a metal. It's a metal that looks like copper, but it's not copper. It's oh goodness, what is brass made of? It's copper and zinc, is it? The two mixed together? Anyways, the most common place you see brass in your home is, I think, for things like door handles and these metal features around the home, like you know, like maybe the leg of a table. If it's metal, it's probably brass. Copper and zinc, is it? Brass? Yeah. Next, copper, which you know. Yep. Next one, steel, which you know. Yep. Next one, this is graphene. Do you know what this one is? Yeah, it's what's inside the pencil. Graphite, yeah. I think there's maybe a small difference. I don't know. I don't know why I use words I don't know what they are for certain. Graphite. Next one. Oh no, sorry, that was the last one. I shouldn't have those boxes there. So this might actually surprise you, but this actually has a higher Young's modulus than steel. Which means if you push it or pull it, its shape doesn't change much. It's difficult to deform. And you know that steel is difficult to deform. You need a lot of force to change its length. So graphite is even more difficult to deform. Okay, let's continue. Do you have all these values? Yes. So, back to the buoy. A buoy hangs a 100-gram mass at the end of a 1.5 meter copper wire, which is attached to the ceiling. The wire is 2 millimeters thick. Okay, so let's draw that. Okay, so here is the wire. It is 1.5 meters. The thickness is 2 millimeters, and then the buoy hangs 100 gram mass at the end of it. Okay, so the first thing, let's do this one now. Part A, and this is copper. What is the cross-sectional area? So what is the area here for this? Oh, it fell out. Yeah, well, what shape is the area of the circle? So we have to use pi r squared. So what's the r here? 1 millimeter. Yeah. So the area is pi r squared, which is pi 0.001 squared which is 0.001234566. Is that right? Yeah? Got that? Continue? So, part B now. What is the stress on the wire? Okay, so this, again, not so difficult. What's the formula for stress?
Force over area.
Force over area. Now, we know the area, but we don't know the force. But, yeah, what is it? mg, because? It's the weight. So it's m, which is 0.1 times 9.81. So let's type that in. 0.1 times 9.81 over 3.1415 times 10 to the power of minus 6. And I get 312271. Well, let me be more accurate. 3.141592654. 312262 pascals. Okay, C. Well, you could probably guess what I'm going to ask you next. What's
Strain.
what is the strain?
Strain is extension over natural.
Yeah. Now here's the small problem. Because, yeah, what don't we know? Well, what do we know? Do we know the natural length? Yeah, it's 1.5. But do we know how much it extended down when we put the weight on? No. So we don't know the x. And we also don't know the strain because that's what we want. But there is still a way to get the strain. What could we do? Yeah, we could use E equals stress over strain. So that means then that strain is stress, which we know, over E, which we also know because I said it's copper. And what is the value of Young's modulus for copper? 117? 9, like this?
Yeah.
So the strain is 2.669 10 to the minus 6. No units. Okay so far? Yep. Now, what am I going to ask next? Well, now I'm going to ask you probably for the extension. Yeah. I want the extension now. So which formula should I use?
Strain.
Well, now I can use this one because I now know this and this. So I can say x equals strain multiplied by natural length. Do I know the strain? There it is right there. What did I say the natural length was?
1.5.
1.5. So if I multiply this answer by 1.5, 1.5, I get 4 times 10 to the minus 6. What's 10 to the minus 6? Micro. Yeah. 4 micrometers is the extension. Yeah. And finally, what is the K for this material? The Hooke's law. Well, we can work that out, but first we need to find a formula. We know E equals F, stress over strain. And we can therefore say F equals F over A equals X over L times E. Did I do that right? Did I?
Yeah.
Something feels wrong. My spider senses are tingling. No, that's right. Goodness. So we can say F equals A X E over L. But I don't really want F. But the reason I did this is because Hook told me F is Kx. So if I just divide out now the X, I can get a formula for K. K will be A E over L. Now that's good because I know the E, I know the A, and I know the L. So let's work out the answer here. What did I say the A was? 3.1415 times 10 to the power of minus 6. What did we say the E was for copper?
1
Okay. And then the L was 1.5. So I get 245 kilonewtons per meter. That's the K.
Why would you do K equal F over?
Oh yeah, you could use that as well. Sorry Bruce, I was being stupid. Thank you Bruce. Let's do it both ways. So there is another way to do this which is easier. I just showed you this because it's the hard way, but let me show you the easy way now. So as Bruce reminded me, F is equal to K over X, and we know the F and we know the X, so we can say K equals F over X, and what is the F? That's equal to mg over X. So let's see if we get the same answer. What's the m here? 0.1. The G and the extension was a 4 micro, was it? Ta-da! Same answer, 245 kilo newtons per meter.
Why Newton? Why Newton?
Why Newton? The K is newtons per meter. Yeah, look here, see? Newtons, meters.
Then over the equation.
Here?
Yeah, over the.
Here?
Yeah.
Yeah, well, have a look here. What unit is A? Yeah, meter squared. What unit is E? And what's a Pascal? Newton per meter squared. And what unit is L? Ta-da! Okay, you got that? Yes. So we have two ways. Continue? Yeah. So, I think that was only one example because that includes everything. So, what I want you to do for just 5 minutes, and then we'll start the next lesson, just try one or two of those questions.